Hello and welcome to another episode of Physics Problem Solving. Today we're looking at a practice question for a quantum subject exam, looking at one-dimensional potentials. Here we have a W potential. I'll give you a second to attempt the problem, and after a short transition, I'll be back and I'll give you the solution. Welcome back. I hope you took a second to attempt the problem. This solution is going to look a little bit different from previous solutions, and that is because if you're seeing this question on an exam, there's kind of a base of knowledge that you have hopefully seen in class. If not, we'll go over it right here. So these are some summary slides from Pablo in his crash course teachings. Basically, we have the time-independent Schrodinger equation, and going through the derivation of solving that in class, you get two solutions. It's these sines and cosines that gives you a negative k squared, and then exponentials, which gets you a positive q squared. Since it's just the second derivative of sines and cosines or exponentials, you get the same term back. And these are kind of general solutions. This is just what we're going to assume solves the Schrodinger equation in all of these regions, which I have labeled 1, 2, and 3 for this specific problem. It's always going to look different, but there's only a few certain variations that most professors can make, and the W potential is one of them. So with that little bit of intro out of the way, we can start on the question. We want to state the general solution for the Schrodinger equation in the different regions of the potential and explicitly specify values of the coefficients k and kappa. I can't really differentiate those over here, so I'm going to call that q, and to stick with the notes down here, in the exponents of your wave function ansatz. So our current setup is defining this region 1, 2, and 3. And we're going to assume that we have the most interesting energy level, and that's going to be somewhere around here, below the 0 but above the negative v naught, so that way we actually have something happening. So in region 1, we're going to have psi of x equals, it's just going to be a sine of kx plus b cosine of kx. For region 2, since we are below the potential, we're going to have psi of x equals c e to the negative qx plus d e to the qx. And for region 3, we're going to have psi of x equals e sine of kx plus f. Oh, let me clean that up real quick. Cosine of kx. And we know that the k's in region 1 and 3 are going to be the same because we have the same v in both of these regions 1 and 3. The only difference that might happen is if you're asked specifically about a scattering solution, so something, let's say at E2, our region 2 is just going to change to sines and cosines. So it'll be c sine k. This k will be different, so k2x, and then plus some d cosine of k2x. And I mean, that's everything. That is the general solution in all of these different regions. We haven't specified anything about these constants, but I'm going to rearrange the board a little bit and show that that is our next steps. On to part 2. How are the coefficients of the general solution restricted for wave functions with even or odd parity? So we have even parity and odd parity defined up here. Even parity is when psi of negative x equals psi of x, and odd parity is when psi of negative x equals negative psi of x. So now it's really just breaking it down. We're going to start with region 2, and we're going to imply evenness of the solutions. So we're going to say c e to the negative qx plus d e to the qx equals c e to the qx plus d e to the negative qx. And so this is now a limitation on our coefficients, and we're going to have c equal to d. And for the odd case, we have c e to the negative qx plus d e to the qx equals negative c e to the qx minus d e to the negative qx. And this then limits our coefficients c equals negative d, because if we match this e to the negative qx, the e to the negative qx on the other side is matched with a negative d. You can also do it the other way around, doesn't really matter. You can now also rewrite these. Since c equals d in the even case, we can say c, all of that, e to the negative qx plus e to the minus qx. And c is just an arbitrary constant, but we can call this combination of exponentials hyperbolic cosine of qx. And then same for the odd solutions, but we end up with hyperbolic sine. And these functions retain their even and oddness. So with region 2 out of the way, we can now look at regions 1 and 3. Since they are on opposite sides of the y-axis, they will mirror to each other. So we're going to be looking at the even case. We're going to do a sine of k negative x plus b cosine of k negative x equals e sine of kx plus f cosine of kx. And with this one, we'll have the signs. Those need to cancel. So we'll have a equals negative e. And we'll have that b equals f. Doing the same thing for the odd solutions, we have a sine of k times negative x plus b cosine of k times negative x equals negative e sine of kx minus f cosine of kx. Again, matching up with the sines and cosines, we get that a is going to be equal to e, and we get that b is going to be equal to negative f. So the last thing we can do to restrict these coefficients is look at the value at x equals b, because we know that psi of b will have to equal 0, since there's no possibility that the wave function leaves this double well potential, since it's infinite on both sides. I have a little bit of insight, so I know that the solution is going to be same for even and odd. If we just look at it, at psi of b, we have e sine of kb plus f cosine of kb. Subtracting one side to the other, we have negative e sine kb equals f cosine kb. Hopefully you can see the relationship already. We have negative E tangent of KB equals F. And you can double check me, but this will be the same for both even and odd solutions. So now we're on to part 3. Determine the matching conditions for psi plus minus of x and their derivatives at the boundaries between potential regions. Hint, because of the symmetry of the potential, it is sufficient to only consider the boundaries with x greater than 0. The boundary conditions for x less than 0 will yield the same relations between the coefficients of the solutions, which can be a useful test. Awesome. So looking again just at our even solutions, we only have one boundary that we haven't considered, and that is at x equal to a. So we are going to set region 2 equal to region 3. So we have c e to the negative qa plus d e to the qa, and that is going to be equal to e sine of ka plus f cosine of ka. And then we also have the derivative conditions. So just taking the derivative of this, we can pull a q out, and we get negative c e to the negative qa plus d e to the qa. And on the other side, we can pull a k out and flip the sines and cosines. So we have a k times e to the cosine kx, and then again cosine has a minus sign, so minus f sine of ka. And that is the matching condition for the even terms. Looking at the odd terms, we can do the same thing. We have c e to the negative qa plus d e to the qa equals e sine of ka plus f cosine of ka. And lastly, we have the derivatives. Again, pulling out a q. We have negative c e to the qa plus d e to the qa equals, again, pulling out a k, e cosine ka. Sorry, that's a minus f sine of ka. Just mentioning again for some clarity, we can also rewrite some of these exponential terms. So we know the even one, this would be a hyperbolic cosine, and that would then make this one hyperbolic sine. And for the reverse case, we have hyperbolic sine, and that would then change this to hyperbolic cosine. Not much changes, but that does allow us to clean up some of the equations using the relationships at the bottom here. And with that, that does complete this question specifically. We could go ahead and solve for the transcendental equations using all of the relationships that we have, but this is sufficient to answer this question. There is one variation on this problem, and it involves a delta potential. So let me draw a quick example. We have this delta of x minus r with some scaling value lambda, and it sits somewhere inside of a, let's say, infinite square well. This will basically just lead to a jump condition, which I have defined as negative h bar squared over 2m. This is the derivative of psi from the right at the value r minus that same derivative, but from the left side at r, and then adding on the scaling factor of the delta function plus or times the value of psi at r, and that equals 0. So that just means that as we approach this delta function, we will have a discontinuity, which is cleanly defined by this equation here. And that is kind of everything that could happen in seeing one of these one-dimensional questions.